All right, so which generically is called leakage current, okay? So again, in an ideal transistor, what you'd like, in an ideal case, so this is gate source voltage versus the drain source current. The horizontal axis, notice it's linear, but notice that the vertical axis is log scale, okay? So if I zoomed out of here, I didn't plot it in a, so if I zoomed out of here, it kind of looked like this. So we're sort of plotting right here. All right. So this is like sort of an on region, saturation region. But notice it looks really small in this graph, but this is like really like 100, 200, 500 microamps. Okay. So this looks like, anyway, you guys know what it looks like. So, okay, so we're kind of like down here in the weeds. And what you'd really like is this is going to do whatever it's going to do, and you hit the threshold voltage, and you go to 0. That's what that first level model says. As soon as first level model says, there's that first level model, it says that if VGS is less than VT, the current is 0. Not small, not a nanoamp, 0. By the way, here's a bit of engineering, a good hint for you guys. There's never such a thing as 0 in the real world, okay? So whenever somebody tells you they want 0 of something, to first order, they haven't told you anything, okay? If they're really mean, like if they're asking you to design 0, you should ask them to, like, there's no such thing as like 0 defects or 0 current or 0 voltage or 0 electrons or 0 photons. I don't know, 0 anything. It's like small numbers, but I don't know any 0 things. I mean, you know, engineering kind of stuff. They could tell you some other zeros. Like how many zeros is in your paycheck? Just kidding. All right. So it doesn't go to 0. So let's talk about it. What does it do? Well, it gets very small, but it has a different slope in this so-called sub-threshold region. Sub-threshold region just means below threshold, okay? Then you might even have some current when your VGS hits ground, and there's some leakage, and there's all these sort of effects, okay? So there are a bunch of leakage effects. Leakage is kind of like having a fever. Like it could be because you got food poisoning, you got a fever. It's because you got COVID, you got a fever. Because you got a cold, you got a... So like a lot of stuff causes leakage. Leakage is bad, and a lot of stuff causes it, unfortunately. So here are the 3 major things. So let's talk about one of them at a time. The first one is so-called subthreshold leakage. And it comes from the fact that when your voltage, the threshold voltage, I made it sound like it's like a solid number, but it's like anything else. It's not a solid number. You're like, as you get towards it, you get lower and lower, and you get below it, and something happens, and so on. But there's definitely like a change in the slope of how it works, of how the transistor works in subthreshold. By the way, for some things, and I've done this myself, so for some devices, like usually medical devices, you might actually, when you're doing analog design, you might actually operate your amplifier or circuit in the subthreshold region to be at really low current. And it's interesting because it gives you a completely different transistor functionality for analog designs, like different transconductance equations and all that stuff. So anyway, and it's got this really It's got an exponential relationship between current and VGS and VDS. Okay, so fortunately for you guys, you do not, for this class, you do not need to remember this. Don't need to remember it. You do need to remember a couple of things though, okay, which are very important. One thing is the way the sub-threshold voltage goes, okay? This is like, I don't know who came up with this, like which deity or the transistor deity, but it works, seems like across the board. This is kind of hard to take in a little bit, is because it's absolute numbers, I'm telling you guys. Every 100 millivolts below V sub t, this subthreshold leakage current, IL whatever sub, goes down by 10x. Okay? So let's say your threshold voltage is at, just as an example, at, let's say at VT, your subthreshold current was 100 nanoamps, and your VT is 300 millivolts. At 200 millivolts, subthreshold current is going to be 10 nanoamps. It's going to be 10 times less. So for each 100 millivolts you're below VT, your leakage current drops by a factor of 10, because this is the slope, 100 millivolts per decade. This is the slope, and it's on a log scale. Okay, so it's reducing fast with VGS below 100 millivolts. Okay, so and then at 100 millivolts VGS, it's at 1 nanoamp. So every 100 millivolts, it goes down by a factor of 10. Okay, you guys with me? Okay, so that's at room temperature, okay? And this is like, this is what you guys should remember. Okay? Okay, so now the question you should be asking yourself is, why do I need to remember that? Because I'm doing logic design. Leakage, we only care about when the transistors are off, so there's nothing transitioning at the gate of these transistors. So presumably their gate source voltage is sitting at 0 anyway, or 0-ish, right? That's the kind of the state these leaky transistors will be in. So I'm always like at the lowest point I can go anyway. So why does this matter? Okay. It matters because you have a choice. Well, first of all, you need to know how this works, and sometimes you have a choice in a process where there are multiple threshold devices. Okay, and this is a very important choice. Okay, so it's a trade-off between speed and leakage. It's a trade-off between speed and leakage current. A very important trade-off. So we haven't gotten to this, but a lot of times, not always, when you have more current, you may have more on current, the faster you are. A lot of times, not all the time. Okay, so you want your on current to be high as possible. Your gate source voltage, it is what it is. You can't go up too high, and for reasons, because of the electric fields and other things. So if I just look at the saturation current, it's dependent on VGS minus VT squared. Right? We just got talking about that to first order. So for a large on current, it's really powerful to have a low VT. Low VT, good for large IDS at on, and therefore maybe for speed. A lot of times, good for speed. So you want low VT to go fast when you're on. Okay? Now imagine if I drop that VT to, so I had a 300 millivolt VT, and the foundry say, hey, let's drop the VT to 100 millivolts. You guys with me? So in that case, when VGS, when the transistor is off, VGS is at 0, okay? Imagine for a case of VT is 300 millivolts, okay? In that case, I am 300 millivolts when I'm off. I'm 300 millivolts below the threshold voltage, so my leakage current is 1,000 times less than at VT. Okay, when my transistor is off, it has 1,000 times less current than at VT. Okay, now let's say I say, hey, I want a faster transistor, so let's make the VT 100 millivolts instead. Okay, so again, when VGS is 0, now I'm only 100 millivolts below VT. So it's only 10x less. My leakage current is only 10x less than at VT. Okay, so I have 100 times more leakage current for transistors that's off that has a 200 millivolt lower VT. Does that make sense? It's a little hard to grasp. You guys with me? No? Yeah.
Can you repeat that one more time?
What's that?
Can you repeat that one more time?
Sure. So did you get the part about how lower VT gets you a more on current?
Mm-hmm.
Okay, so that's good, right? Now, let's say that sort of 10% of the chip is on, chugging along. The rest of the chip is off. The gate source voltages, let's say they might be 0 or something like that. So you have a low gate source voltage, but then you want to calculate what the leakage is of these off devices, okay? Now, if these devices have a high threshold voltage, their leakage currents are going to be a lot less than if they have a lower threshold voltage. And that's because for your VGS, when the transistor is off, the VGS is always 0. Okay? VGS is always, so input voltage is always 0 volts, right? For an off MOS, say. So it's always 0. So then the question is, what was the VT? How do I calculate the current, the leakage current at 0? You got to figure out how many 100 millivolt increments is 0 below VT. Because for every 100 millivolt increment, your leakage current goes down by a factor of 10. That means if your VT was 100 millivolts, 0 is only 100 millivolt increment. Your leakage current is only 10x lower than what it was at VT. Okay? Let's say if your VT is 300 millivolts, now you're 1,000 times less than you were at VT. Okay? So you're off, the higher your VT is, means the higher your VT is, the more off your transistor, your off transistors are going to be more off the higher VT is. Does that make sense? By 10x for every 100 millivolts. Okay, which means pretty sensitive. Very sensitive. So you have this trade-off between going fast and having low leakage. Okay, so it's a trade-off you have. Okay, so what do people choose to do about that? So a lot of the times in the process in the CMOS models you guys have, you only see one threshold, but a lot of times the foundries offer, like almost all the time, you at least get 2 threshold or sometimes 3 threshold devices. You get, but once the threshold is set, it's set. So you tell the foundry the way you do the layout, or you build it up. I want these guys to have this threshold, I want these guys to have this other threshold, and this stuff to have this other threshold. Usually it's two or three thresholds, so it might have like a high threshold NMOS transistor that might have a 500 millivolt threshold, and then you're gonna have a fast transistor, so VTH fast NMOS that might have a 200 millivolt threshold, and some VTH mid that might have 300 millivolts. I'm just making these up, but those are the kind of numbers you see. Okay, you guys with me? So what you do, again, fortunately, most of the time, only a few of your circuits need to be really, really, really flying fast. Okay? Your signal paths, your memory interface, those need to be fast. You guys familiar with I2C or SPS, or like some serial interface, or something that controls some accelerometer, or something that controls your microphone? Those don't need to be fast, right? So for those circuits, when you design those circuits, use the high threshold devices. So when they're off, they're really off, and the speed, you wouldn't have noticed the speed anyway. They're not really doing anything fast. And you save your low threshold transistors for those signal paths where you really need them. Okay, so that's what effectively this means, yeah.
Is there a cost difference between the low threshold and high threshold?
No, the thing is, no, not really. Sometimes there's a cost difference in how many flavors you ask for, sometimes there's just only one flavor, like they just say, you get all three, like it or not. Sometimes they say, well, it's lower cost for if you just use one, and higher cost if you use two, and higher cost if you use three, mostly in the mass cost. But normally, from what I see, they just sort of get it. It's not a big difference in cost anyway, if there is small. So, yeah. Guys with me? Also, it tells you why the foundries, like you can't just go to 0 threshold voltage or 10 millivolt threshold voltage. You just don't see that, right? Because you could say, well, look, how come my power supplies are stuck at 700 millivolts or a volt? You said you want